Good morning. My name is Dr. VLS Banu, Professor Civil Engineering Department in Lord's Institute of Engineering and Technology. Today I am going to give a talk on matrix method of analysis, introduction, flexibility matrix and stiffness matrix, example of flexibility matrix method of analysis. Coming to the introduction, a structural system may be defined as an assembly of members with the purpose of transmitting external loads of the surrounding environment onto the foundation. The stability of a structure depends on the number and the arrangement of internal members and also the external reaction components. If a structure is stable under the action of forces acting on a plane, three conditions of equilibrium must be satisfied. They are sigma h equal to 0, sigma v equal to 0 and sigma m equal to 0, means where sigma h is the algebraic sum of all the horizontal forces in the x direction and sigma v is the algebraic sum of all the forces in the vertical direction, must be equal to 0, and sigma m is the algebraic sum of the moments of all the forces about a point, must be equal to 0. Coming to the flexibility matrix and the stiffness matrix, in a system having a single degree of freedom, the displacement d can be expressed in terms of the applied force P by the relation d equal to F into P, in which F is the flexibility defined as the displacement per unit force. F is the flexibility which is defined as the displacement per unit force. On the other hand, the force P can be expressed in terms of the displacement d by the relation P equal to Kd, in which K is the stiffness defined as the force per unit displacement. The structural systems invariably have multiple degrees of freedom and are subjected to several loads. In this case, the displacements may be expressed in terms of the forces by the matrix equation D equal to F into P. On the other hand, the forces may be expressed in terms of displacements by the matrix equation P equal to K into D, in which the matrices D and P respectively represent the displacements and the forces. The coefficients of flexibility matrix F are the displacements per unit force, whereas the coefficients of the stiffness matrix K are the forces per unit displacement. These equations may be written in the matrix form as matrix D equal to matrix F into matrix P. This equation may be written in the compact form as D equal to F into P. We will see an example on the flexibility matrix method of analysis. The below given figure is a continuous beam of two spans, span AB and span BC, and it is subjected to 2 point loads of 240 kilonewtons and 120 kilonewtons. The total number of reaction components are 5. In the given continuous beam, the total number of reaction components are 5, means 3 reaction components at the fixed support A, 1 reaction component at the roller support B, and 1 reaction component at the roller support C. So altogether total we have 5 reaction components and we have 3 equations of equilibrium. So 5 minus 3 equal to 2. So the degree of static indeterminacy of the structure is 2. Now coming to the flexibility matrix method of analysis, we need to release the degree of indeterminacy is 2. So we need to release 2 reaction components. Let us say I release the reactions at B and C. When I release the supports at B and C, the released structure will be a cantilever. The displacements at coordinates 1 and 2 due to the given external loadings may be computed as follows. Next, we need to find out the displacements at coordinates 1 and 2. The points where we have released, those points are to be named as the coordinates. So in our case, we have 2 coordinates, coordinate 1 and coordinate 2. At these 2 coordinates, we need to find out the displacements. The displacement at coordinate 1 equal to delta 1L. Let the displacement at coordinate 1 be delta 1L, be the displacement due to the 2 point loads at coordinate 1. So delta 1L equal to delta 1L1 plus delta 1L2. The displacement at any point in a cantilever beam due to the point loads is given by the formula Wx square into 3L minus x by 6EI. Delta 1 L1 is the displacement at coordinate 1 due to 240 kilonewtons. So this is a cantilever beam AB. It shows only coordinate 1 and also a point load, only one single point load, 240 kilonewtons. Now what is the displacement at coordinate 1 due to the point load of 240 kilonewtons? That value is nothing but we are representing it as delta 1 L1. So the formula for computing the displacement is Wx square into 3L minus x. So substituting the values of L and x, where L is 10 meters, x is 5 meters and W equal to 240 kilonewtons. So substituting all the three parameters, we get delta 1 L1 equal to 25000 by EI. Now in the same way, we'll find out delta 1 L2, where this parameter is nothing but the displacement at coordinate 1 due to the second point load. Second point load is of 120 kilonewtons. So in our case, in the second case, W equal to 120 kilonewtons, L equal to 15 meters, X equal to 10 meters. So delta 1 L2 equal to Wx square into 3L minus x by 6EI. Substituting all the values for W, L and X, we get delta 1 L2 equal to 70000 by EI. So adding up both the displacements at coordinate 1 due to point load of 240 kilonewtons and also due to the point load of 120 kilonewtons, we get delta 1L equal to 95000 by EI. Now the displacement at coordinate 2, let delta 2L be the displacement due to the 2 point loads at coordinate 2. So delta 2L equal to delta 2L1 plus delta 2L2, where delta 2L1 is the displacement at coordinate 2 due to the first point load of 240 kilonewtons, and delta 2L2 is the displacement at coordinate 2 due to the second point load, that is 120 kilonewtons. The displacement at any point in a cantilever beam due to point loads is given by the formula Wx square into 3L minus x by 6EI. So delta 2L1 is the displacement at coordinate 2 due to 240 kilonewtons. So W equal to 240, L equal to 20 meters and x equal to 5 meters. Substituting all the values in the formula Wx square into 3L minus x by 6EI, we get delta 2L1 equal to 55000 by EI. In the same way, delta 2L2 is the displacement at coordinate 2 due to 120 kilonewtons. So W equal to 120 kilonewtons, L equal to 20 meters and x equal to 15 meters. Delta 2L2 is nothing but the displacement at coordinate 2 due to the second point load of 120 kilonewtons. That is given by 202500 by EI by substituting all the parameters of W, L and X in the equation Wx square into 3L minus x by 6EI. We get delta 2L2 equal to 202500 by EI. So the total displacement at coordinate 2 is delta 2L equal to delta 2L1 plus delta 2L2. So when after adding up these two displacements at coordinate 2 due to 2 point loads, we get 257500 by EI. So the displacement matrix. Now we have found the displacement matrix. Displacement matrix D equal to delta 1L by delta 1L is the first parameter and delta 2L is the second parameter of the matrix. So substituting all those two values, we get the displacement matrix D. Next, we need to frame the flexibility matrix F. The flexibility matrix with reference to coordinates 1 and 2 may be developed by applying a unit force successively at coordinates 1 and 2 and computing the displacements at these coordinates. Means we frame the flexibility matrix by applying a unit force at coordinate 1 and 2 successively, and we need to find out the displacements due to this unit force. So the size of the flexibility matrix is 2 by 2. Since we are solving for two coordinates, we have two coordinates 1 and 2. So the size of the flexibility matrix also will be 2 by 2. So coming to coordinate 1, F11. Now we try to compute F11. F11 is the displacement at coordinate 1 due to the load at coordinate 1. So the formula will be WL cube by 3EI. This is nothing but a cantilever beam having a unit load at the extreme end. And the formula for finding out the deflection is WL cube by 3EI. So F11 equal to WL cube by 3EI. That is nothing but 1000 by 3EI. Next parameters are F12 and F21. This flexibility matrix is a symmetric matrix. So F12 and F21 parameters will be the same. So the displacement at any point on a cantilever beam, the formula is Wx square into 3L minus x by 6EI. So substituting all the parameters, we get F12 equal to F21 equal to 2500 by 3EI. Now the next parameter of the flexibility matrix is F22. In this case, we apply a unit load at 2 and also the displacement at 2. So the formula is WL cube by 3EI. So substituting all the parameters, we get 8000 by 3EI. So F equal to F11, F12, F21 and F22. We know all the values of the parameters of the flexibility matrix. So substituting all the parameters, we get the above matrix. We get this matrix. Okay, D equal to F into P is the formula for the flexibility matrix. P equal to P1 and P2. Now we know the displacement matrix and also the flexibility matrix, but we need to find out the force matrix P. So the force matrix P equal to F inverse of D. So we get all the parameters of the flexibility matrix, inverse of that into the displacement matrix, we get the force matrix P. And after solving that, we get P equal to P1 and P2, P1 equal to 199.3 and P2 equal to 34.3. These two, P1 and P2, are nothing but the reaction components at B and C, where B equal to 199.3 and the reaction component at C equal to 34.3. So now we need to analyze this. Means we need to find out the reaction component at A, that is RA. So the reaction component at RA we can find out by equating sigma V equal to 0. Sum of all the vertical forces is equal to 0. So RA plus sum of all the vertical forces equal to RA plus P1 plus P2 equal to 240 plus 120. So RA equal to 126.4 kilonewtons we get. Now we need to find out the moment at A also. So taking sum of all the moments of forces about A, then about R, the reaction component at C, that is P2 into P2 is 34.3 into 20 plus 199.3 into 10 minus 120 into 15 minus 240 into 5. Solving all this, we get 321 kilonewtons meter, minus sign with a minus sign. So minus sign means the moment is acting in the anti-clockwise direction. The moment is acting in the anti-clockwise direction. So the above is the reaction components for all this. Yeah, thank you.